Okay, I think it's good now, hopefully. I will try not to bump it. Okay. Thanks, guys, for coming to the review. Good to see you all here. I assume that you're getting that take-home quiz finished up, and hopefully that's going well. Oh, good. The screen is on. So we're going to do some practice problems today. I'm going to kind of overview the material a little bit for the exam. Remember, the exam is not until a week from Monday, but we've covered now most of the material. There are a couple of topics that we haven't gotten to, and I'm going to get to those, of course, next week. So we're doing pretty well in that sense. So in terms of the exam, we've got, of course, Chapter 4. Except for 4.7. And that's going to be the bulk of the exam. I mean, it's a big chunk of it. I would say somewhere, I have not written the test yet, so I can't give you any exact percentages, but I would say somewhere 55 to 65% of the test is what I'm expecting it would be. Chapter 5, which is much shorter, might only be 25 to 30% of the exam, and then Chapter 6, we're only doing 6.1. That might just be 10 to 15%. So the sections that we have not yet covered are 5.3 and 6.1. We'll be talking about both of those in class on Monday, primarily. I may give you a quick heads-up preview about those sections today if you want one. Otherwise, I'll just focus on the stuff we've already covered and practice that, and then leave the rest of it for later. So let me go ahead and a quick little overview about Chapter 4. Chapter 4 is about vector spaces. And just a quick rundown of some of the things that you should be able to do with vector spaces. You should definitely know the definition. So, the 10 axioms that we learned. So this would be A1 through A10. Okay? So you want to know the axioms of a vector space. In particular, the ones that are the most important are the closure under addition and scalar multiplication, which are the first two axioms. So I'll just say including closure under addition and closure under scalar multiplication. Those would be the two most important ones. You should know the primary examples of vector spaces. So Rn is the easiest one that everybody learns first. And then Pn of R, these are polynomials of degree n or less. And then the n by n matrices, that's Mn of R. And then finally the m by n matrices, which means that your matrices may not be square sized. So these are the primary examples, and then we also have, thank you. Then we also have C of AB. This is the vector space of functions, which is a very important family of examples as well. So anyway, so these are like the big umbrella universes that sort of all of the problems that we're looking at come in. And you probably have noticed by now that as you go from one problem to another, you kind of go between these different vector spaces. There might be a problem about polynomials, and then the next problem is about matrices, and then the next problem is about traditional vectors, and then you get a problem about functions, right? Kind of cycling through, and we're looking at all of our concepts, things like linear independence, basis, spanning sets, and so on, in each of these different worlds to kind of hopefully unify our understanding of the concepts in a variety of different contexts. So these are good vector spaces to be very familiar with. But what really comes up more frequently than these examples are the subspaces. subspaces are really important. Mitchell, you're going to have to sit way over this way. Thank you. So subspaces, if I say something is a subspace, I'm really just saying it is a vector space. A vector space is a subspace, but it's within one of these larger vector spaces, right? So you're always inside of one of those. So a subspace is just, you have to have closure under addition and closure under scalar multiplication. If you check these two things, if you check closure under addition and scalar multiplication, then you will have a subspace. The rest of the axioms get inherited by S, by the subspace, from the big universe vector space that you were working with. There are some cases where you can give a fast analysis, and I just want to remind you about this because I will want you to be able to do this, but you can do a fast analysis in certain situations. So in particular, if there's no zero vector, so if the zero vector is not in S, then you do not have a subspace, right? So you can check that zero vector. That's usually the first thing I like to do. If the zero vector is not in the set, then you don't have a subspace. On the other hand, if S is equal to a span of something, so if we have the span of something, well then, I don't care what's in those parentheses, a spanning set is always a subspace. I mean, a span of a set is always a vector space. Closed under addition, closed under scalar multiplication. And also, the other case that's a very fast analysis would be if you're talking about the null space of a matrix. So if S is equal to the null space of some matrix capital A, well, then the answer will be yes. Okay, so we're going to be practicing this today a little bit. So these are some situations on subspaces where you can say a fast yes or a fast no. When something is a subspace, and it's not a span, it's not a null space, then you're going to have to actually check directly that it is closed under addition and scalar multiplication. Right? If something is not a subspace, you have to convince me why. By the way, I'm not going to be giving any points for just circling yes or no. Right? I have to have a justification that goes along with it. So if the answer is no, you could use the zero vector justification. But if the zero vector is in the set, then you would need to use an actual example to show that it's not closed under addition or scalar multiplication. Right? Yes, Captain.
Would you have to show that they're both not closed under?
No, so if either of these two closures fails, then you do not have a subspace, and you can stop. At that point, you don't have to check the other one.
But if the zero vector fails and closure under, no, or I'm sorry, say the zero vector passes and then closure under addition passes.
Mm-hmm.
Is it possible we still could get it to pass? To fail?
Yeah, yeah. You have to check every single thing, right? Until you find something that is wrong with that example, you still have to keep going through it. So we're going to do some examples to kind of point that out here in just a few minutes. Exactly. Okay, so I think everybody needs to be familiar with these standard vector spaces, as well as how to show that something is or isn't a subspace. This is the sort of at the beginning part of chapter 4. Okay, so subspaces is a yes or a no. Sometimes there's a write-up that you have to carefully produce, and sometimes you can give a fast analysis. It just depends on the problem. Okay? As we get a little bit further into chapter 4, the next main thing that you need to be really comfortable with is the idea of a basis. And along with basis is the concept of dimension. So these are some of the highlights of the middle of chapter 4. Basis and dimension. Remember that a basis, if you are talking about a basis, there are two primary attributes that you're looking for. Your vectors have to be a spanning set, and your vectors have to be linearly independent, right? And so you have to kind of remember how to verify a spanning set and linear independence. The question that I often like to ask, in fact it's one of the ones on the take-home quiz, is I give you 4 choices. Is S a spanning set? Is it linearly independent? Is it both, or is it neither? Both just means it's a basis, right? So, but this is again yes or no, right? This is again yes or no, and the way that we generally verify whether it's yes or whether it's no is by making a matrix. We lay our vectors out into the columns of a matrix, right? So you have a set that is proposed as a possible spanning set and a possible linearly independent set, and you lay them out in the columns, always the columns, and you augment that matrix with either numbers or with zeros. The numbers is to check the spanning part, and the zeros is to check the Li part. So this is what you're trying to do. Okay? Everybody remembering all of this? Kind of just reviewing what I hope everybody is mostly comfortable with. The dimension is easy. It's just the number of vectors that are in the basis. So once you write down the basis, then telling me what the dimension is just immediate. You can get that figured out immediately. Okay, so this is really 4.4, 4.5, and 4.6. Right, those 3 sections. 4.4 is on spanning sets, 4.5 is on linear independence, and 4.6 is on basis, where you're kind of putting everything together. Right? I also want you to remember this important thing about the relationship between the number of vectors that somebody gives you and the dimension of the space that those vectors are in. So if K is bigger than the dimension of the vector space that you're looking at, which I sometimes call N, if K is bigger than that, then the set V1 through VK, right? If I give you, in other words, if I give you too many vectors, then this is not Li for sure. You can immediately conclude that you have too many vectors for linear independence. On the other hand, if K is less than the dimension of V, okay, in that case, these vectors do not form a spanning set. It is not a spanning set for V. Okay, and then finally, if K is equal to N, if K is equal to the dimension, if I give you the right number of vectors, then this set is both or neither. Okay, so I give you a vector space, and I give you a proposed set of vectors to span that space. This is just the 3 possible scenarios between the number of vectors and the dimension of the space, and that determines, by the way, this is not a spanning set for V. So it's not Li, not a spanning set, or it's both or neither. And on this one, you can actually put the vectors into a square matrix. As soon as it's a square matrix, you can take the determinant of it and decide whether it's 0 or not. If it's not 0, that's good. It means it's going to be both. If it is 0, then that's bad. It means it's going to be neither. Okay. Great. So this is kind of the middle. So this is the first part of chapter 4. This is the middle part of chapter 4. And then the last part of chapter 4 is about specifically looking at a matrix, let's say an M by N matrix, and studying these null spaces, row spaces, and column spaces. So a row space and column space and null space. And again, the absolute comprehensive review of what you need to know about this is on the bottom half of that handout that I passed out in class. right? So it's not much. There's not much there, but you need to know, like, what is the null space, right? It's just the set of vectors in Rn that solve the system Ax equals 0. That's what the null space is. So you're literally solving a linear system of equations to find a null space. And of course, this will always be a subspace of Rn. It's closed under addition and scalar multiplication. It's a subspace of Rn, and its dimension is called the nullity of the matrix. So the nullity of A is the dimension of that matrix. Okay? The row space is the span of the rows of A. You're taking the span of the rows of A. Remember, if you take the span of anything, you always get a subspace. So this is a subspace. This one is also a subspace of Rn. So it is a subspace of Rn as well. And the dimension of this one is what we usually call the rank of the matrix. So the rank of the matrix is just the number of pivots, because remember that the basis for the row space, is just the pivoted rows of the row echelon form. So how many vectors is that going to be? It's going to be the number of pivots. Right? So that's the rank of the matrix. Okay? So even though the null space and row space are both subspaces of Rn, they may not have the same dimension within Rn, right? Because these are subspaces of that space. So they could actually be smaller. Does this make sense? Yes? Okay, great. The column space is, similarly, is the span of the columns. So this is the set of the span of the columns of A. And the thing that's different here is that the columns are going to form a subspace, the span of the columns is a subspace of Rm, not Rn. So this is a subspace of Rm. And the dimension of the column space is also the rank, because you're just going to, remember, the way you find a basis for the column space is you row reduce your matrix, you examine where your pivots are, which columns those are, right? And you grab the corresponding columns from the original matrix, and that's the basis that you're going to report for the column space. So how many vectors is that? Well, it's one per pivot, right? Each pivoted column creates a vector that's in the column space, and so again, the dimension is the rank. This is a little confusing sometimes, because what you're saying here is that even though the row space is a subspace of Rm, and the columns, sorry, the row space is a subspace, this is an n here. The row space is a subspace of Rn, the column space is a subspace of Rm, but the two spaces have the same dimension within those larger, remember the Rn is just some big umbrella universe, right? It's not actually the space that you care about. The spaces that you're caring about are these spaces in this context. Okay, and then one last thing that relates all of this together in a very simple way is the number of pivots, which is the rank of the matrix. The number of pivots in the row echelon form plus the nullity, which is the number of free variables. Those are the columns without pivots. If you take the pivots plus the non-pivots, you always get the total number of columns of the matrix. Right, so that is the rank nullity theorem, and that's also on that handout. So between the handout kind of covers all of this. This is the last part of chapter 4. It covers all of that, and it also covers this little business here as well. Okay, so between that and then the earlier stuff on spanning sets, you've got a lot of materials to look at to kind of review this part of the course. There's also, one last thing was the invertible matrix theorem. invertible matrix theorem here. This is right at the end of chapter 4. There was no homework on this. I never asked you to do any problems on it, but just knowing the statements, you know, A is invertible, and then just kind of, we kind of skip over the first few parts. We go down to statement G is about the determinant. And then I just want to remind you to kind of, I mean, a good test of how well you're understanding the material, really, honestly, is whether you truly understand why H, I, J, K, L, M, N, and O are also true for an invertible matrix. So I'm not going to write them all down again here on the board, but this is something in your notes from, I guess it would have been from Monday. So on Monday we would have made that list of the statements in the invertible matrix theorem. If you ever lose track of that theorem, by the way, it's in the back cover of the book. So the very back page here, this list, it actually goes all the way down to S, but we haven't quite gotten that far yet. So we've done kind of A through O so far. Things like when the matrix is invertible, the rows are linearly independent. The columns are linearly independent. The rows span Rn. The columns span Rn. The rows form a basis for Rn. The columns form a basis for Rn. That's a lot of what these statements are about. It's all good things, right? An invertible matrix is a good thing. Having a basis, linear independence, and a spanning set, those are all good things. So we're kind of thinking of them all together at once. Okay, so this is an overview of chapter 4. Kind of the beginning of it, the middle of it, and the last part of it. Okay, are there any questions on the overview so far? Just kind of want to get it into everybody's heads before we start throwing some problems at you. Okay, if everybody's good with that, I am going to give you guys quite a few problems on chapter 4. So I'm going to wait to do the overview of chapter 5 and 6 until later. I want to get through, this is about 2/3 of the exam is on chapter 4. So let's do some problems on chapter 4 for a while, and once I feel like I've talked about most of the topics that are important, then we'll move on to the other chapters. Okay, so here's an example of a problem, and this is actually coming from the group work, but I don't think anybody did this problem in the group work, so I thought, well, I'll just do it with you guys. Okay, so a couple of quick little proofs. So there will be some theoretical problems on the exam. I haven't written it yet, but I know I will ask you something that you have to explain it. So prove, or explain, in other words, if A is an M by N matrix with the column space of A equal to the null space of A. So imagine that you have a matrix where the column space and the null space are the same. Then I want to explain why M has to equal N. And this does not have to be long. It's just going to be, this. If I put this on the test, this would be worth like 5 points or less. It's not a big, long explanation that you need. But we're saying if the column space and the null space are the same, then M is equal to N. So you just need to stop and kind of pause, take a breath, think about what is the column space, what is the null space, and what do I know about them. So I've got it kind of on the board over here, right? The column space, what is it? It's the span of the columns, okay. The null space, well, that's the solutions to this system, right? What else do I know? Oh, the column space is a subspace of Rm. The null space is a subspace of Rn. So there's the M and the N coming into it. Okay, so does anybody have an explanation for me? Maybe want to try an explanation out on this one?
If the null space is equal to column space, that means that there's the same number of pivots as unpivots.
That's true.
Okay.
That is actually true. Yeah.
So,
That's addressing the dimension aspect
Right.
of it.
I know, I'm working on explaining it.
Yeah.
think
So
this is on
let me
the
ask you,
quiz.
how many slots are there in anything that's in the column space?
And number of slot,
Say again?
And
M
and
slots, right?
Okay.
Look at the column space is a subspace of Rm.
Uh-huh.
So there are M slots in anything here. How many slots are there for any of the vectors that are in the null space of A? N slots, right? And we're saying that all of these vectors make up a set that's the same as all of these vectors. In other words, this collection of M slots and this collection of N slots has to consist of the same things. Well, that means that M and N have to be identical. They have to be the same. So you just have to write that out, right? The explanation is easier than you might think. You just simply have to say that since the column space of A is a subspace of Rm, and the null space of A is a subspace of Rn, well, then since they are equal, by assumption, we're assuming that they're equal, well, therefore M equals N. That's all you have to do. Just that short. Yeah, Kevin?
So then sometimes for these types of questions, you don't have to prove it algebraically.
Right, right. The proof, in fact, I probably should use the word explain here to just explain. It's not always an equation. It's more of an explanation. It's almost like, think like how you would do a true-false type. You say true or false, and then you give an explanation. Yeah. Let's do another one. Let's practice another one that's kind of similar. So let's do this one. This is also another proof. Prove that if A is an n by n invertible matrix with the row space of A equal to the null space of A, then A cannot be invertible. Isn't that interesting? So this time it's a square matrix. So we don't have the difference between the m and the n. It's a square size, and I'm going to assume that the matrix, oh, I wrote something wrong.
yeah, it's an invertible and
Yeah, hold on. I miswrote it. Yeah. Sorry. Take out the word invertible here. Yeah, that didn't make any sense, did it? So if A is an n by n matrix with row space equal to the null space, then A cannot be invertible. That's what I meant to write. Sorry about that. Okay, so if we have a square matrix and the row space and the null space are the same, then that matrix cannot be invertible. So let you guys think about it for a minute, and maybe then we can have some time to talk about the ideas here. Do you have an idea, Renee?
yeah.
Okay.
So, because for an invertible matrix, the null space is equal to 0. So
Ah, that's right. So somewhere over here in this list of the invertible matrix theorem, for an invertible matrix, the null space is just trivial. Right. So if A was invertible, let me write that down. If A is invertible, then its null space would be trivial, right? So then null space of A is literally just only the 0 vector. Okay, that's in that list of the invertible matrix there.
And then would that suggest that there's 0 unpivoted columns?
So that would suggest that there are 0 unpivoted columns, exactly. So in other words, we can also just say that the nullity of A, which is the dimension, remember the nullity is the dimension of the null space, that would be 0. And if the nullity is 0, then what is the rank? It's n, right? So the rank of A is equal to n by the rank nullity theorem. So this isn't looking very good. This isn't looking very good because if A is invertible, if A was invertible, now we're saying the null space is tiny, but the rank is huge. The rank is, of course, the dimension of the row space. So we're saying that the row space, this is the size of the row space, right? So thus, the dimension of the row space, the dimension of the row space of A would actually have to be n now. Well, how can something that's n-dimensional be equal to something that's 0-dimensional? It's impossible, right? So I'll just say which is impossible. We'll just cut to the chase here. This is an impossible situation because you're saying that what you're saying is right. If you have an invertible matrix, it will have a tiny null space and a massive row space. So, in other words, they can't be equal. They can't be equal. For sure, they're not equal. Does this make sense? Okay. So these are kind of little, exercises that you can play with to kind of practice, some sort of baby proofs, I guess you could call them, about some of this stuff. Okay, let's go on to something else. I'll come over here. Let's do some subspaces, some subspace questions. I think this usually, it takes a little practice to get good at writing these up. So I'd like to do that right now. Okay, so let's do some examples here. Is S a subspace of V? So let me try and write down some examples for us. Let's take the first one here, part A. Let's use the 2x2 matrices as our vector space. And I'm going to let S be the set of A element of V. So in other words, I'm going to take the 2x2 matrices such that the entries of A are all non-zero, or A is equal to the zero matrix. Let's just try this one and see what you guys think of it. S is those matrices where the entries are all non-zero, or the matrix is just the zero matrix itself. And I'm asking, is that a subspace of V? What's the first question that you usually want to think about, or the first thing you want to address when you're asked a question like that? We check on the zero vector. Exactly. If the zero vector is not in the set, then the answer is no. We could just cross it off immediately, right? So the zero vector here, so I'll start my solution right here. The zero vector in this case, of course, is just the 2x2 matrix of zeros. And is that an element of S? The way I wrote it, it is, because I gave that as an option here. It could be that A is equal to that matrix. So we just put a check there. This is good for showing your work. It also kind of shows me that you know what you're doing. I can give you some credit for recognizing that step. Okay, if it passes the zero vector check, then we have to start thinking about, and we need to do the thinking before we do the writing, about whether this is a yes or a no. The thing is, if it is a subspace, then what we're going to be writing down is going to be a generic proof to show it. And if it's not a subspace, then I need to give an example of closure under addition failing or scalar multiplication failing. So what is your gut feeling? We have to have before we write anything down, we need a gut feeling. Do we think that this is closed under addition? If I take two matrices that have no zeros in them, so matrix A has no zeros in it, matrix B has no zeros in it, do you think that after you add them together that it will still have to have no zeros in the result?
No.
No.
I don't think so either. I think there's going to be an example we can make,
Yeah.
right? So if we think that we can make up a counter example, then what we're going to write here is closure under addition fails, right? So we have to explain that. And to show that, I want you guys, when something fails, I want a very specific example. So can somebody give me an example of a 2 by 2 matrix that would be in S?
A equals 1, 2, 3, 4.
1, 2, 3, 4. Excellent. So we take 1, 2, 3, 4. That is definitely in S. Okay. Can somebody give me another matrix that would also be in S, such that after you add it to this one, the result is not in S? 4, negative 2, 3, 9. Excellent. Let's try it. So there's a matrix, there's a matrix. These are both in S. However, when I add them together, 1, 2, 3, 4, plus 4, negative 2, 3, 9. When I add them together, what do I get? I get 5, 0, 6, 13, right? Is this in S? Are all of the entries non-zero? No. No, so this is not in S. That's what I want to see, like a really specific counterexample. Okay? When something fails, a counterexample is the way to convince me. Do I need to spend any time thinking about closure under scalar multiplication? I don't have to, right? I already know that S is not a subspace. I already know that S is not a subspace of B. I can stop right there. Just out of curiosity, do you think that this would be closed under scalar multiplication? If you took a 2 by 2 matrix, where the entries are all non-zero, or you take this matrix and you scalar multiply by a constant, do you think you would get either this or this?
Yeah.
Yeah, you would, right? Because if the constant was 0, you would get this. If the constant was not 0, then when you multiply it by all of these non-zero entries, you'll get another matrix that has no zeros in it again, right? So actually, this is irrelevant really, but just as a note, just as a side note, closure under scalar multiplication actually holds. It's okay. The closure under scalar multiplication part would actually have been okay. All right, let's try another example. Come back over here. Let's do a part B. Okay, so part B. Okay, so for part B, I'm going to take V to be C of 0, 1. So this is the calculus functions that are defined on the interval from 0 to 1. And I'm going to let S be the set of functions in V. So I'll write it as F, little f, an element of V, such that 0 is less than or equal to f of x is less than or equal to x for all x in the interval 0 to 1. Okay, so this is, same question that we asked before, but this time we're doing it in the context of a function space. It's a function space that we're looking at here. So this is a little different. We haven't done one quite like this. So your function is sandwiched between 0 and x. So my first question is going to be about the 0 vector. So does everybody understand this vector space? The basic idea here is that you only, the domain of this function is just the interval from 0 to 1. You just have this closed interval from 0 to 1. And the vector space V is just all possible functions that you could draw on the interval 0 to 1. So is this, but the set S is those functions where the function is positive, but stays below the line y equals x. By the way, the line y equals x would be approximately like that, right? That's y equals x. So what we're talking about here, guys, is S consists of all of the functions that sort of stay sort of below this line, right? And they don't go below the x-axis. So they're kind of sandwiched in here. And my first question is the 0 vector in that set? It absolutely is. It's just this vector right here, right? The 0 vector in this case is just the function that is right on the x-axis. So I'm just going to make a note that 0 is an element of S. The 0 vector is an element of S. So we've got that. What do you guys think? Do you think that this is going to be closed under addition and scalar multiplication? So if I take, let's think about the two parts of that. So you're saying if I take two blue curves here and I add them together, if I take two functions that are both underneath that line y equals x, is it true that the result will stay underneath that line? Getting different answers here. So I have to think about it a little bit.
Yeah, I think so. Because if you added any of them, like say you added the two bottom vectors, right? It would be some vector in between those two. When you added the two.
So if I added this one to this one,
yeah.
well, I'm going to be taking this one and I'm going to be adding a little more to it. So it's going to go up higher.
Okay.
Right?
Yeah.
So it's going up higher, and I'm a little nervous now that it might punch through that line y equals x, you see.
Okay, so what about like, oh, is this where we would have to use that function in to do the calculus function? Or would we just say like f of x plus g of x? Say if let g of x be another matrix? Okay.
Well, it's not a matrix. So basically,
Oh.
you're taking two functions and you're just adding them together.
Okay.
So it's like taking e to the x and adding it to sine of x, right? What is the result of that? Well, the answer is it's e to the x plus sine of x, right? So just in that very fundamental framework. Renee, I'm interested in talking to you because you said you think the answer is no. So which of the two parts do you think fails, or both of them maybe?
When you add them together, because if you have a function, for example, of a cubic, and you do f of x equals x cubed plus f of x equals, or g of x equals x cubed, you get 2x cubed.
Okay, so x cubed is in the set because x. So by the way, this is the point 1, 1 right here. Right, so that's a y value of 1. So x cubed, the graph of x cubed goes something like that, right?
Yeah.
Of course it continues, but we're only looking at the part of it that's on 0, 1. It goes kind of like that. So that's definitely in the set, okay? However, so you want to double it.
Yeah.
So can I change your justification to scalar multiplication then?
Okay.
So if we take 2 times that expression, 2 times x cubed, what does that look like? Well, I'm just going to, first thing I realize is that when I plug 1 into this, I get 2. So this cubic is actually going to go way up outside of the bounds of this line, right? So in other words, 2x cubed is not in S because the output of the function In other words, what we're saying is that 2x cubed is bigger than x. For example, if you just put something like, I don't know, 0.9 would be an example. You take 0.9 cubed, multiply it by 2, I promise you it's bigger than 0.9. So, therefore, this is not an S, so this fails. Okay, so S is not a subspace of V. Make sense? Okay, let's do another one. Let's do another example here. This is part C. Let's do V is equal to R5, and S is equal to the set of X, Y, Z, U, V, such that X plus 2Y minus 2U plus 3V is equal to 0, and negative 4X minus 8Y plus 8U minus 12V is equal to 0. So my big universe is R5, and I'm looking at those 5 tuples that satisfy this equation. And so my question here is the same one. Do you think that S will be a subspace of V?
Yes, because it's already set to the null. It's already set to the null space.
Okay.
Or we can find the null space from. I don't know if I'm saying this.
Well, S is the null
S
space
is the null
of a
space
matrix,
of a
and
matrix.
what I would want you to do to justify this, you're absolutely right. When you see a system of equations that are all equal to 0 here, it's a thumbs up, right? It's a subspace. If any of these equations was not 0, then the answer would be no, because the 0 vector. No, we would know that it's no, because if I change these numbers over here to something else, like, 4 and 5 or whatever, well now, the 0 vector doesn't work. Then you can just say that.
There's no
Right.
0 vector.
There's no 0 vector, so it's not a subspace. But if I put zeros here, I'm glad that, did everybody catch this? That this is really just a null space, right? So this is a yes.
But then we would have to give you what the null space is.
Yeah, I would suggest that you do that. So because, let's get the justification, because S is equal to the null space of, and then your job that you would need to do would be to write down the matrix. So can somebody tell me what the matrix would be? And thank you for noticing the 0. That was a little trick. There's no Z in the equation, right? Okay, and how about the second row? There you go. Okay, so the missing variable, the Z here, I chose to leave it out to see if everybody would catch that there's a column of zeros in that matrix. But it has 5 columns because it's a subspace of R5. Okay?
So then, if the columns didn't agree with the Rn, and the linear system still were equal to 0, would it not?
So what he's saying is, suppose I put like a W here, and then I put like a minus 8W plus 7W or something, right? This would not be a subspace of R5. It would be a subspace of R6. That would be a trick question where I give you something that doesn't have the right number of slots. So this has 6 slots, and that says R5 on it. So there would be no, this is like apples and oranges if it was like this. So yeah, that's a good point. That would be sort of me being kind of tricky about it, and I don't see why I would want to do that. But anyway, that's a good observation. Yes?
In the case where the null space only contains the 0 vector, we still call that subspace?
Yeah, that's the trivial subspace. The
Okay.
0 vector by itself is the trivial subspace, and that can happen. For example, the null space of an invertible matrix is always just 0. only 0.
That's dimension 0 then.
And it has 0 dimension. Yeah, that's right. That's right. Actually, so let's do a follow-up. On all of the earlier examples, the answer was no. We did not have a subspace, so we had to basically call it quits. But once we have a subspace, I'm going to ask you a follow-up here. The follow-up is to give me a basis and dimension for S. So follow-up, find a basis / dimension for S. Let's see if we can figure out how to do that. Okay. Anybody know what we need to do to do that?
For the basis, we would have to find if it's Li, and we would have to find if it's Li and.
We need a. So what's the other part of the definition of a basis? It's linearly independent and it's. Say again? Spans. It's a spanning set.
Spanning set.
So it's a spanning set that's linearly independent. Now, in this case, we don't have a proposed basis. We're being asked to find one. So if I gave you a list of vectors and said, are they a basis for the null space, then you could throw them into the columns of the matrix, augment with number symbols or with zeros, and do the usual procedure following the calculation. Row reducing the matrix, looking at which columns have pivots, and doing the analysis. Here, we don't have any vectors at all that have been given to us. We're sort of starting from scratch, and they're saying find a basis. So how do we do that?
You augment it with 0.
Exactly. We take the matrix A, that I'm going to call this A, by the way. This is the matrix A. We're going to just take that matrix and augment that matrix with zeros. So that's going to be 1, 2, 0, -2, 3, augmented with 0. And then -4, -8, 0, 8, -12, augmented with 0. And what do we do with it? Row reduce it. Exactly. So we're going to row reduce it. The first row is already beautiful. The second row actually just wipes out because it's -4 times the first row. So we can wipe that out. And what do I do next? I have 4 free variables. Which of my variables would be considered the free variables? Y, Z, U, and V, right? Those are the free variables. So I usually like to use what do I usually use? R, S, T, I'm running out of letters. And we could use W. Okay, fine. So we use W for that. And then we can solve for the leading variable X in terms of that. So we go back to this first equation basically and solve for X. So it's going to be -2 times R, and then +2 times T, and then -3 times W. Okay, in terms of our free variables. Okay, great. So we've got that done. What am I going to do
Bust out the variables.
next? Yeah, I have to bust out the variables of this, don't I? So I know, I get excited about it too.
It's about the only thing I can do right.
You
so
like to
far.
do that.
Yeah.
It's something that comes up a lot.
Is there anything, okay, besides spanning set, where we bust out the variables, is there anything else, any other points I can promise myself, because I can remember?
Oh, no, this is the main thing where you're busting out variables.
Okay, so it doesn't work for anything else?
It doesn't really get used for anything else.
Okay.
Okay, so we have R, S, T, and W,
This one's on
which are
this.
real numbers. This is just writing the null space down. I haven't busted the variables out yet. I just wanted to show what it looks like as a set. And now I can bust out the variables. And when I bust out the variables, I have 4 of them. I bust out the R, and I obtain what? -2, 1,
0,
0, 0, and 0. Great. And then the next one is S. S is being multiplied by 0, 0, 1, 0, 0. Good. Then I have T.
So 2, 0, 0, 1, 0.
right? 2, 0, 0, 1, 0, and then finally we have W.
Negative 2, 0, 0, 0, 1.
Right, so negative 2, 0, 0, 0, and 1, and then of course this is still such that R, S, T, and W are elements of R, and your basis now is just those 4 vectors.
So we
In a
pull them
list.
out and
We
we
pull
put
them out.
span and then we write the vectors, right?
Yeah, we don't even need to write the word span, we just write basis equals,
Okay.
and we just list the vectors. So it's just gonna be negative 2, 1, 0, 0, 0. Then the next one is gonna be 0, 0, 1, 0, 0. The next one is gonna be 2, 0, 0, 1, 0. And the last one is negative 2, 0, 0, 0, 1. Okay, there you go. By the way, so those are definitely a spanning set because every vector in the null space is a linear combination of these 4. If somebody pressed you about linear independence, I would just comment.
Isn't that 3W and 3?
Oh no, I messed up. This is a minus
It's
3W.
on all of them actually.
What's that?
It's on all of them.
I screwed it all up. Now you tell me. Yeah, this should have been negative 3 right here. This one should have been negative 3 right here. Does that look better? Okay.
Like, I looked up at my notes, like, oh.
Yeah, that's not quite what you have. Yeah, okay. That's right. So I had a little typo there. Anyway, if somebody asks you, are these linearly independent or not, because you're saying it's a basis, they have to be linearly independent. The way you would test that is by, well, of course, just putting them into the columns like that. You would augment over here with zeros for linear independence, and you would realize that you actually have no free variables left because every single column is going to have a pivot when you do your EROs. So they are linearly independent, they are a spanning set, so this is a basis. Okay?
And then our dimension.
Yeah, so what is the nullity of this? What is the dimension?
The nullity is 0.
No, no.
Oh,
It's the number of free variables, which is?
4.
4. Exactly.
And also our number of vectors.
It's just the number of vectors
And-
in the
yeah,
basis. Yeah.
okay.
So you just look at the basis. The dimension of a vector space is always just the number of vectors in any basis for that vector space.
Okay.
Yeah, Kevin?
Question for that, the top one, null space.
Uh-huh.
Would it be wrong if you wrote that like, the first one, comma, and then?
Oh, wrote it in a row instead of a column?
Yeah.
That would be okay. That would be okay. The reason I like to write it as a column is because when you're thinking about this null space equation here, right, you've got a matrix here, and you're going to be putting the matrix there, and this X for matrix multiplication, it makes sense to view it as if it was a column.
Because it
Okay.
could be like, since that's a vector, that could be x1, x2, x3.
Yeah, it has slots in it.
Okay.
And so it just visually, I think of it as a column normally, but if you wrote it out as a, in fact, if you check the back of the book on some of the answers to some of the problems, to save space in the writing in the book, they will often put the vectors as rows instead of columns. So either one is okay.
And also to follow up,
Mhm.
if you were to write the dim of S equal to 4, would that be?
That's also fine, yeah, that's the dimension of S. The dimension of S would definitely be 4.
Okay, so for the nullity and the dimension stuff, right? So for example, because when we did our null space and we came up with our basis according to the null space, because we have 4 vectors and vectors, and also because we can also see that we don't have any free variables.
Right.
And we have 4 pivots and no free variables. So
Well, yeah, for checking these guys for linear independence, you have 4 pivots and no free variables. Of course, back here, in this original matrix, I only have 1 pivot, and I have 4 free variables. So this is the rank nullity theorem. The rank is 1 for this matrix. The rank is 1, the nullity is 4, and 1 plus 4 adds up to 5, which is the number of vectors, or number of slots, right? So
Okay.
R5.
So that n is that n that we say our rank for our rank nullity term.
Yeah,
that
that's-
n that it equals. That's the same n that we say, because when we say m by n, that's our rows by our columns.
Correct, yeah.
And then so
this is
initially
a
we
2
had
by
5
5
columns.
This is a 2 by 5 matrix here.
Right, but we
Yeah.
didn't actually have our n does equal 5.
Yes.
Oh,
The
okay.
n does equal 5.
Okay.
Yeah. Absolutely. Okay, is everybody good with that? All right, yes, Kevin.
Just sorry, is that like possibility for questions is like you can ask one thing but then ask for like 10 different things?
I could ask a follow-up, is that what you mean?
Yeah.
I could say, now if,
But
Is
then
it gonna be the type that if we get it wrong the first
I
time? it's
probably will
insurance?
not, okay, so I'm very careful about this, because I know that, let's say that you said that, no, this isn't a subspace, and then you get to part B, and you're like, oh, well, wait a minute, it doesn't make sense. Because you can't ask about a basis and dimension unless something is a subspace. I am much more likely to just simply say in part A, show that this is a subspace. Then you would do that, and then you would then go from there to part B. And even if you didn't do the closure under addition correctly, or even if you didn't notice that it was a null space, you can still do part B, because you can still do the augmenting of the matrix and row reducing it and so on. So I really try hard. It's not always possible, but I try very hard to write questions that are independent from one another, so that if you aren't getting the right thing in part A, you can still do part B.
So
Or if you do part A and you don't do it correctly, I take what you gave me in part A and I look at how you used it in part B and say, well, based on what they thought the answer was, they've done the rest of this correctly, and then I give those points on part B. In fact, I give full credit.
yeah.
And the answer might be wrong, completely wrong on part B, but I give it full credit if it's based on using an answer that maybe I took points off on part A. I don't like to double penalize people on multiple different parts, so.
So like the first midterm, because I think the first question you asked like a matrix, and then the second one was like, oh, is that matrix invertible or something?
Right, I did, but those were disjointed questions, right? Because you can go straight to that second question and analyze it even in the absence of the first one.
And I got the first part wrong, but you gave me a point or two for circling the no. Even though my
Yeah.
explanation was not quite right because I didn't get the right part, but because I attempted to according to
To what you had said, yes.
Yeah.
That's what I'm always trying to do, so.
So I have another question. So if there's no subspace, then there's no basis or dimension question.
Right. There's nothing else you can do.
Okay.
Once there's no subspace, it's game over. It's like, there's no other follow-ups. It's
Okay.
kinda.
And then I know we're just focusing on chapter 4 for right now, but is inner product spaces a subspace?
Yes, because
Okay.
an inner
So-
product space is a vector space.
Yeah.
So it is.
So then,
That's true.
once we get to inner product spaces, the same thing applies. If we decide it's not
A subspace.
of the vector, then there's no dimension.
Right.
Okay.
Right.
Cool.
Absolutely. That's still, all of that is still true in chapter,
And inner product space is just a dot product.
more or less, yes.
More or
But
less.
it could be in other contexts.
That's right.
Yeah. So we'll come back to that in a second.
I know, I just.
Oh, you have to get going. Oh, okay. Well, let me do a few more. I mean, chapter 4 is the most substantial part of this. So let me do another question. Is this good on subspaces for now? I had a couple more I was going to do, but maybe I'll move on and then come back to it again later if there's more time. I just don't want to lose all of our time on just one part of it. So let me go on to a different type of problem here.
Will we post these examples?
Well, these are in the review sheet.
Oh, okay.
Yeah, so we're going over it right now, as a matter of fact. So let's do this one. Let's let V equal M2 of R. Actually, let's not do M2 of R. I'm sorry. Let's do the other one first, which is a little more. Let's do P3 of R. And let's let S be the set 1 plus x plus 3x squared plus 3x cubed, comma, x plus x squared, comma, 2 minus x plus x cubed, comma, negative 3 plus 6x plus 6x squared plus x cubed. And what I'm going to do is ask you whether S is linearly independent, whether it's a spanning set, whether it's both, or whether it's neither. Okay, so is S Li neither. Let's try and do that. Give everybody a chance to copy it down and think about it for a minute. So we have 4 choices. The thing with this is that you always can cross off 2 of the choices immediately with no further thought whatsoever. And the way that you can do that is by just looking at the dimension of V and the number of vectors. What is the dimension of P3 of R?
4.
It's 4, correct. So we have the dimension of P3 of R is equal to 4. And what is, I usually call it K, what is the number of vectors in the list? It's 4, right? There's 4 polynomials there. So what that means is that these match up. When they match up, guys, then the correct answer is either both or neither. So I can cross off Li and spanning set. It's going to be either be this one, both would mean that it's a basis, neither would mean that both
LD.
Properties fail. It's LD and it's not a spanning set.
So that's easy enough. If we already crossed off Li and span and we're only saying both or neither, the easiest thing to do would probably be check for LD at this point. Because if it didn't, then we could just say.
Well, how do we proceed from here?
Open a matrix.
Right. We're going to put these vectors into a matrix. How do we put them into the matrix? Always into the columns of the matrix. So what I'm going to do is I'm going to set up, to answer this question, I'm going to set up the first polynomial into the first column, and I'm just grabbing the coefficients, 1 and 1 and 3 and 3. The second one has no constant term, a 1 on the x term, a 1 on the x squared term, and no x cubed. The third one is a 2, a -1, a 0, and a 1. And the last column would be -3, and then 6, and then 6, and then 1. It's a square matrix. So you can actually avoid, okay, so we can augment this with, number symbols to check span, or we can augment it with zeros to check Li.
Or the determinant.
Right, if it's a square matrix, guys, just the bells should go off. I can just take the determinant of that. Okay, would you guys mind if I just tell you what the answer is? Because this is a 4x4, I'd rather not, I probably won't ask this on the exam because a 4x4 determinant would have been something I would have asked on the first midterm. It's really a chapter 3 question. You have to do, obviously choose a row or a column and do cofactor expansion. But I think for the time being, I would rather not spend 15 minutes doing that. And I'm just going to tell you, you can check it. By the way, the other thing you can do is do EROs and keep track of the effects on the determinant as you do those EROs. You're going to find out that it's 0. Actually, in a minute, we're going to do the EROs anyway, because I'm going to have a follow-up question. Anyway, the determinant is 0, which tells you which of these is the correct answer.
Neither.
Right. So it's neither. It's not a vector space. Sorry, it's not a basis at all. It's not linearly independent. It's not a spanning set. So now I would like to throw a couple of very interesting follow-ups at you that are based on this. So the first one, if you're saying that it's neither, then you're saying that the vectors are LD. So follow-up number 1 is find a linear dependency. So follow-up here. The follow-up. So the first one is find a linear dependency.
Oh, I'm glad we're doing this because I went through all my notes and I thought I remembered us doing this in class, but I couldn't find it in my notes, and so I thought it was crazy.
Well, we're going to review it.
So I'm glad that we did actually do this.
Yeah, we have done this, okay? So we're going to find a linear dependency, and then there's going to be a second follow-up, so I'm going to write them both down first. The second follow-up is this. I know that if I take the span of S, I'll get a subspace. I know, however, that that subspace is not the whole V, because we've already said that no, it's not a spanning set for V. So the question then becomes that this is it does form a subspace, so there's got to be a basis for it. Find a basis. Find a basis for the span of, I'm just going to write span of S. It just means all four of these guys. Okay, so we're going to do these two questions.
So we're saying it's not a spanning set for that vector, but it's obviously a spanning set for something.
It's a spanning set for whatever it spans.
So we'll find out then. Okay.
And then the question is, all right, it's a spanning set, but it needs to be a basis. S itself is not a basis for anything, because S is, right, it's just a set of vectors, because S is LD. If it's LD, it's not a basis, so we're gonna have to work on it a little bit. So let's do these one at a time. How do we find a linear dependency? You know, if we, let's say we didn't even know if there was one. I know we've already taken the determinant here, but let's imagine that we didn't know whether these vectors were Li or LD. What we would do is we would make this matrix, right? You would just make this matrix, let me write it down. Just recopying the same exact matrix again. So we would just write down this matrix, and what would we augment the matrix with in the far right column?
Zeros.
All zeros, exactly. Okay, and what we would do is we would do EROs and reduce it to row echelon form. And what I'm hoping is that you guys will allow me to just tell you what the row echelon form is, because the ERO part of it is kind of repetitive of what we already know. So what will happen when you row reduce this is, I will just tell you what you get so we can focus on the conceptual part. You're going to get the second row changes a little bit, and the third row changes a little bit more. So 0, 0, 1, negative 2. And then, of course, the last row has zeroed out. This is another way of figuring out that this is a neither situation. Because you have a, notice, here's your pivots.
You have a free variable.
You have a free variable. That means that your vectors are LD. That last variable is usually called C4. Remember, we have constants here that are associated with these columns. Right? We associate these constants with these columns.
Okay.
And so the point is that C4 is free. I'm just going to call it T. And if I now do back substitution, I can start to figure out what C3 is. So C3 minus 2T is 0. So that means that C3 is 2T. Okay. And then C2, again by back substitution, it's going to be, what is it going to be? It's going to be 3 times C3, that would be 6T, and then minus 9T. That's negative 3T. Are we getting this, or am I going too fast on the back substitution?
Negative.
So you see that? So like this, in the second
plus
row,
9T. Okay,
right,
negative
C2 minus 3C3 plus 9C4 is 0. So if you put T right there, and you put negative 2T right there, and you start solving that one, I'm sorry, C3 is 2T, but this is 2T. So if you put 2T there and T there, then you've got C2 equals negative 3T, right? And then finally, you have to back substitute for what C1 is. C1 is negative C2 times C3 plus 3 times C4. I believe that's just negative T. So again, this equation is C1 plus 2C3 minus 3C4 equals 0. There's the equation. And if you solve that for C1, you're going to get 3T minus 4T, which is negative T. Okay, now for linear dependency, what do I do next?
Write it out with our C1V1.
We will write that out in a second, but before I do that, there's one other thing I should probably do first.
Well, we're spanning, so we'll do
So we're trying to write down a linear dependency.
Okay.
And it's gonna have the form a constant C1 times V1 plus C2 times V2 plus C3 times V3 plus C4 times V4 equals 0, right? So it should, so the linear dependency, let me just actually start writing it down. The linear dependency should look like this. It should be C1 V1 plus C2 and V1, sorry, V1 is just, we can just put the polynomial here, 1 plus x plus 3x squared plus 3x cubed plus C2 times V2, which is x plus x squared, plus C3 times V3, which is 2 minus x plus x cubed, plus C4, which is times negative 3 plus 6x plus 6x squared plus x cubed, and all of that is going to be equal to what?
Yeah.
0, exactly.
I feel like I would have started, if I was looking for the linear dependency, maybe I would have started there.
And that would be okay. You could start here, and actually if you start here and you start matching the constant terms up and the x's up and so on, you'll end up with this matrix again.
Okay.
And you'll end up doing the same
I
thing
see,
here.
I see. Okay.
But there's one more thing we should do to actually finish this part of the follow-up. Exactly. We just found expressions for C1, C2, C3, and C4, but I should actually plug numbers in. So in other words, what I need to do over here, guys, is I need to choose a value for t. Right? Now, what kind of a number do you want me to choose here?
1.
Anything except 0. If you choose 0, you're going to get in trouble, because then everything's going to be 0, and that's not going to give you the linear dependency. So let's choose t equal to 1, and then what I'm going to do, if you've got your eraser with you, I'm going to start plugging in what C1, C2, C3, and C4 are. So C1 will be negative 1, because it's negative t, so there's a negative 1 there. And C2 would be negative 3, so this just becomes minus 3 times that vector. And then plus 2 times the third polynomial. And then plus 1 times the last polynomial. Okay, does that make sense that that's what we would have? You can check it, like you can actually like work this out and make sure that it all cancels out to 0, but you know that that's what has to happen. It has to cancel out. Okay, is everybody comfortable with that? Kevin?
Is this where, are we showing the coefficients are equal to 0?
No, the coefficients are not 0. There are the coefficients. I mean, if these vectors had been Li, then the coefficients would have been 0, but these are LD. So you're doing a linear dependency in this example.
So for linear dependency, you find the free variables and then
yes,
you make them.
which there has to be free variables.
That's what linear.
And then you plug in numbers for those free variables. That's exactly how it works. Is this good? People feeling okay about it? Let's look at the second part of the question. It says find a basis for the span of S.
So that would be our answer for linear dependency?
Yeah, this is the answer for part A.
The
Yeah.
whole.
Just this whole thing right here.
Okay.
Yeah, you have to write the whole thing down, actually.
Okay.
Okay, yeah, that's it. Okay, so let's talk about part B. I'm going to do it right here. A basis for the span of S. So I know that the span of these vectors is not P3 of R. It's smaller than that. So my basis, I mean, these 4 vectors, these 4 polynomials, are already a spanning set for whatever they span, right? In other words, before I even take a breath, they're already halfway to being a basis.
Yes.
A basis is a spanning set that's also Li. The problem is these vectors are LD, as we've already decided. So how am I going to give a list that would be Li?
We use we just knock off that last column there.
The guilty party is number 4, right? This column is where the free variable was. If it wasn't there,
Oh,
we would not have had a free variable.
yeah.
And if that wasn't there, it means this wasn't there.
Uh-huh.
And for this to not be there would mean that we didn't have this polynomial. This polynomial has created the problem, right? So we just throw it away. We just throw it away and we write our list here. The basis is going to be, the first vector is 1 plus x plus 3x squared plus 3x cubed. And then the second vector is x plus x squared. And then the third one is 2 minus x plus x cubed. And the last one, oh, that's it. We don't have the last one. We're dropping the last one. And so this is now your basis. The dimension of the span of S is only 3. I love to put this kind of question on a test. I'll say, I'll give 4 vectors. I'll put 4 vectors there. I say, what's the dimension? And you know right away that people that don't know what's going on will just say 4 right away with no justification. But it's not just a simple matter of counting how many vectors you have. If they are LD, as we saw that they are, then we needed to throw one of those vectors away. In this case, 1. Sometimes you have to throw away more than 1. Any unpivoted columns at all have to be discarded. That's the idea. Does this make sense?
Can we write the basis as the pivot? Like 1 and then x and then 2 minus.
Oh, 1 and then x and then 2 minus 3x plus x squared as the basis. No. You have to go back to the original vectors here. It's kind of like when you calculate. You're welcome. It's kind of like when you find a basis for a column space of a matrix. You can't just take these pivoted columns. You have to go back to the original columns up here. Yeah. So yeah, you would need to go back and grab these for sure. Okay. Actually, so if you actually wrote out these columns as polynomials again, so if you wrote this one down as 1, and you wrote this one down as x, and you wrote this one down as 2 minus 3x plus x squared, I know that that's not a basis for S, because it doesn't even have an x cubed in it anywhere. But look at S. S has lots of cubic terms, right? So that you would not expect this to be a basis for the same thing. Okay, so you have to throw that away. Yeah, Kyle.
Sorry, but on the linear
Dependency?
yeah.
Yeah.
The coefficients up front, do they have like a significance to that? Like
No, it's just all based on what you chose t to be. If I chose t to be 10, then all of those coefficients would be 10 times bigger.
But are we saying that we can make up, like, because it's t, like we can make those up with all the, like.
I mean, you can choose anything you want for t. So if I chose t to be 10, then I would have negative 10 here, negative 30 here, 20 here, and 10 here. It would still be correct. It's still a linear dependency. It's not the same one that we originally came up with, but it's just as valid. It's with different coefficients in front of it.
No, I think what I'm trying to say is, like, you know how when like linear combinations, when you can make one thing from another thing, are we saying that we can make those
Well,
that's the
you
form
could-
that we can use to make other linear dependency things?
Yeah, you could rewrite the equation. You could say solve for this polynomial in terms of the other 3 if you wanted to. But you don't have to. This is perfectly good.
But that's like
It's
what
not the only way to write the answer though.
But that's what like linear dependency like means, right?
Mm-hmm. Linear dependency is C1v1 plus C2v2 plus C3v3 and so on equals 0 without all of the constants being 0. That's the key. The constants are not all 0. If you go back to the definition of linear independence, the constants must be 0 in order to cancel those vectors out in a linear combination. So linear dependence is the opposite. It means that I can cancel my vectors out in an interesting way. In this case, I put in these numbers in here. Okay. Are we good on this? Let's see how I'm coming along here. I feel... So in terms of the review session questions, I'm not gonna do, well, let me do one more real quick of the same thing. This one will be faster. I won't do a follow-up. And then I wanna move on to the other chapters. Do my best to wrap this up on time. It's always hard. I get excited. So let's imagine, let's do the same thing with this problem. So let's take V to be M2 of R. And let's take S to be the following matrices. 1, -3, 6, 1, comma, 2, 1, 0, 4, comma, -1, -1, 2, and 1. Okay, so let's take that set right there. Okay? And I want to ask the same question. Are those vectors Li? Do they span the space? Are they both, or are they neither? Okay. Now what's your first thought here? What? Okay, K is equal to what here? 3 vectors, right? And what is the dimension of V, which is what I sometimes call N? What is that here? It's N squared, 2 squared is 4, okay? Okay, so K is less than that, right? So it means what? Right, that S does not span V. So is S Li span set both or neither? So what we know right now is that it's not a spanning set and it's not therefore both. The only question is, are these vectors Li? And to decide that, just like on the last example, you're going to put your vectors into the columns of a matrix. Just do it in an organized fashion. So the first vector, I'm going across the first row, 1, -3, and then 6, and then 1, into a single column. The second vector is 2, 1, 0, 4. The third vector, -1, -1, 2, and 1. And what do I augment this matrix with here? For Li, when I'm testing for Li, I augment it with all zeros. So that's what I'm doing. I'm testing this collection of matrices to see whether they are linearly independent. So this is what I would do. Now, when you start row reducing this one, you cannot take a determinant here because the coefficient matrix is 4 by 3. It's not square. So I have to do the EROs. When I do these EROs, the first row, of course, stays the same. If I take 3 times the first row and add it to the second row, I'll get that. And when I take -6 times the first row and add it to the second row, I'll get that. And when I take the negative of the first row and add it to the last row, I'll get that. Okay? I'm not done row reducing the matrix yet, but I actually have already got a pretty good idea. Because I can tell that when I take, for example, if I do A23 of 12/7, I'll get a 0 here, right? I'll get a 0 here, but this one will not be 0. So this is going to end up, your pivots are going to end up like that. If that's the case, what's the correct answer here? Right. This is Li. It's a linearly independent set. Exactly. Okay. Yeah.
Could you have, from the beginning, kind of just noticed that it would be a lie?
I don't think so.
No? Okay.
No, I don't think, the question is, can you just tell from the beginning that these are Li? I think it takes a little bit of work to figure that out.
But for the other ones where it's like your columns are too long, your columns are too long for your rows, and it'd be...
Yeah, you can tell right away that this is a tall, skinny matrix, so it's not going to span the space. Exactly. Okay. Well, I've done a lot of stuff on chapter 4. I think I'm going to call that good for now. And I'm going to turn off my recorder and then turn it back on for chapter 5. So then we'll start talking about chapter 5.